Thank you very much for the kind introduction. I'd like to first briefly start by introducing myself. My name is Tommaso Marcato, and I'm carrying out my PhD research in the Lab for Interface Engineering of Nanomaterials at ETHZ Zurich, led by Professor Shi, who's now in the audience. And I'm very excited today to be able to present a big part of my PhD research, which I entitled Development of Quantum Dot LEDs, Breaking the Light Outcoupling Efficiency Limit. In recent years, quantum dots, or more broadly, semiconductor nanocrystals, have emerged as a very promising technology for optoelectronic devices, especially light-emitting devices, which are one of the major focus of our research group. And this is due to some very interesting photophysical properties. To name a few, well, quantum dots are bright and narrowband emitters, which means they have a very high color purity. We saw already yesterday in Professor Monkman's talk how important that is for display applications. Not only that, but these photophysical properties are usually either size dependent or composition dependent, which means it's quite easy to tune them, and they are compatible with solution-based large-scale manufacturing processes. And as quantum dots are getting better and better, they started penetrating the market. And you can find them already in some consumer products, like some Samsung QLEDs. Even though it's important to state that in those products, they only appear as passive color converters to enhance the gamut coverage of the pre-existing panel. What we mean by quantum dot LEDs are actually devices where the quantum dots are the active electroluminescent species. They are the emissive layer. And among all the possible materials that you can make it a quantum dot, we mainly study lead halide perovskite nanocrystals, which after three days of conference, I don't think we need to introduce further. Maybe one thing which is interesting for nanocrystals is that we already heard of their unusually high tolerance for defects. Well, that's very handy to make nanocrystals because we can synthesize high quality, so high PLQI lead halide perovskite nanocrystals under quite mild conditions, like room temperature, even in one-pot synthesis. But what about quantum dot devices? Well, here I reported a probably non-exhaustive list of recent very high efficiency devices that's been reported in the literature among the three most promising material platforms, which are cadmium selenide, indium phosphide, and lead halide perovskite. And as you can see, a lot of devices are now breaking the 20%, even 25% barrier, more or less across the whole spectrum, apart from deep blue. And that means that these materials and devices are reaching their maximum potential in terms of internal quantum efficiency. Which that's what motivated us to look into the next big efficiency bottleneck of LEDs, which is light outcoupling. We already heard a bit about, and it's a bit of a tricky one because it's an intrinsic limit of planar light emitting devices. It has to do with that light, so photons are generated within a material, which by definition is denser than air, so total internal reflection is unavoidable. And of all the photons that you generate, only a subset, those whose angle lie within this extraction cone, can effectively be counted as output photons, and that limits the efficiency. Of course, over the past, let's say, 30 years of OLED research, for example, a lot of strategies have been implemented to try and improve light outcoupling efficiency. And I divided them in broadly two categories: what I call extrinsic or external strategies, which usually are characterized by the addition of additional layers in the device stack, which has the specific function of helping extracting light, like a scattering layer. But roughly 10 years, a bit more than 10 years ago, in the OLED community, people started realizing and using what I call an intrinsic strategy for improving light outcoupling, which has to do with transition dipole moment engineering or emitter orientation engineering. And we heard a bit about it from Professor Brütting seminar yesterday. I just share my view on it. So let's suppose, right, you have a molecule here with HOMO-LUMO. We think of it as a two-level system. And we ask how this molecule emits light. Well, the electrons are excited from HOMO to LUMO, and during this excitation, upon transition, there is a charge distribution happening in the molecule. And this is a sort of transient polarization of the molecule, which then relaxes and emits light. And we usually model this as a classical dipole, so as a classical charge, classical current, which oscillates in time. And one striking feature of dipoles, classical dipoles, is that they have an inhomogeneous radiation pattern. They do not emit light the same all around them, but they emit preferentially in the direction which is orthogonal to the dipole itself. And people soon realized that, well, if I somehow manage to orient such transition dipoles in the plane of an LED, for example, I would be effective maximizing the light which is going out of the device, thereby enhancing extraction. And this has now been a staple of high-efficiency OLED, maybe for 10 years, across all the generations of OLED materials. And this has to do with a key point, which was the understanding of a link between transition dipole moment orientation and some molecular parameter, like molecular shape. We heard quite a bit about it, molecular shape, moment of inertia, temperature, right? Because now, for example, let's say molecular shape and molecular orientation, this is something we can control by deposition parameters, temperature, and so on. And at this stage, we started asking the question, can we learn something from it? Can we apply similar strategies to nanocrystals? This together with some preliminary results, both in cadmium selenide nanocrystals, actually nanoplatelets, and lead halide perovskite nanocrystals, which showed that these materials exhibits emission anisotropy, and so these are promising candidates. So here briefly how we quantify emission anisotropy. We use this anisotropy parameter, which was already briefly discussed in some other seminars, which basically quantify as two equivalent representation. It quantifies the fraction of power which is emitted by horizontal, so in-plane dipoles, or can be looked at it if I consider an ensemble of molecules. Well, each of them has their own orientation, so their transition dipole moment orientation. I take the average angle. Well, with respect to the normal, if this angle is some like 90 degrees, it means that most molecules are lying in the plane, and this parameter is then 1. Okay. Well, what we wanted to really start understanding is, can we apply this in devices? Can we give a more comprehensive view of why this is happening in nanocrystals? And to do so, we need to look a bit further into this parameter. Well, if you think of this parameter as the fraction of power emitted, we can expand the power emitted. Here I use just simple Fermi-Golden rule, and we can have a look what we can manipulate of this expression. Well, first thing is the underlying electronic structure, of course, of the nanocrystal. And this is where the biggest differences with respect to molecule lies, because, well, a nanocrystal usually contains a lot more atoms. It has usually high symmetry, which leads usually to a band edge, which is highly degenerate. It means that the states which participate to emission is not only one state, it's multiple states, each of them independently emitting with their independent transition dipole. And this very easily leads to an isotropic emitter. So this is something that plays in it. But next, maybe a bit more interesting, we see that the power emitted by a state depends, of course, on the coupling with the electric field. That's what generates the emission. But not every electric field, the electric field inside the nanocrystal. And this is something I'll show. It's a strong function of the shape of the nanocrystal and its dielectric environment. And we can hope to do something about it. And third, of course, let's suppose we have such a nanocrystal which has an isotropic TDM orientation. In order to achieve emission anisotropy from the film, we need to control how the single nanocrystal assemble together in the film. They need to preserve the order by assemble in an ordered manner. I will present briefly like two, let's say, case studies. We will start tackling the problem for weakly confined nanocrystals, which is a simpler problem because these are nanocrystals where the electronic structure does not change with respect to bulk, or not significantly. So we can disregard this effect and focus on the dielectric environment. This is briefly why lead halide perovskite is an isotropic emitter. This is briefly representing the banded states, and isotropy comes from the conduction band. Conduction band is actually six states, but you can think of them as like 3 states, which have p-like symmetry, like the p orbitals. So they effectively behave as 3 orthogonally oriented dipoles, thereby leading to isotropic emission. So what about the shape? How shape affects the electric field inside of it? Well, we carried out some simulation and we discovered something interesting. Well, if you take, for example, a nanoplatelet shape where only one dimension is confined with respect to the other, what you obtain is an entity, so a nanocrystal, with anisotropic polarizability. In particular, the electric field inside, this is the ratio between the electric field in the plane and the electric field out of plane. You can see it's greater than 1. What does it mean is that electric field in the out of plane direction, so where the nanocrystal is thin, it's effectively much more screened than the in-plane one. And that's important because it means that even if we have a nanocrystal with an isotropic underlying electronic structure, its shape can generate an effectively anisotropic distribution because it will effectively damp the out-of-plane dipole, which are the one we want to kill. And this linked very well together with the observation still from our group that we could achieve quite a huge degree of control over the aspect ratio of MAFA lead bromide nanocrystals by playing with the chain length of the primary alkylamine ligands. So we had a way to use this shape, even in weakly confined nanocrystals. So we synthesized them, and the next problem we had to face is order assembly. So we had our individual nanocrystals, which we believed had anisotropic emission, but at the beginning, right, if you just take this solution and you drop cast on glass, we always measured by angle-dependent photoluminescence just an isotropic emission. So, of course, because you can see here is the predicted anisotropy of the film, depending. So you see, you have the maximum if all the nanocrystals lie horizontal, but if you play with the assembling film, you have, of course, a huge variation. You can achieve a completely isotropic emitter. So at the end, we were able to direct the assembly of this nanocrystal by spin coating on top of a low surface energy whole transport layer. And we observed emission from like an anisotropy factor up to 75%, which means 75% of the dipoles are in plane. And the next step was, let's use this system in LEDs. And in our group, we fabricated quite efficient LEDs based on the system, which reached up to almost 25% peak external quantum efficiency. And through the model I described before, we were effectively able to link the shape and the dielectric environment of the single nanocrystal and how they assemble in the film with the anisotropy factor, which in turn can be used to calculate light outcoupling in ZHAWs, right? And so we can predict what the effect is that on the let's say an estimate of the external quantum efficiency. Next, the last case study of my presentation is, well, what happens if we have strongly confined nanocrystals, where the electronic structure gets significantly modified, the emission gets significantly modified. Well, you cannot ignore the details of the electronic structure anymore. And it turns out what we could use is we implemented a 4-band effective mass model, which was recently developed specifically for lead halide perovskite nanoplatelet. And what this model have understanding is what is the effect, actually like the mixing between these 3 states, which form the conduction band of the nanocrystals. It's shape dependent, okay? So as I depicted here, this is like TDM anisotropy factor is like the oscillator strength of the state. Well, it turns out in lead halide perovskite, if you decrease the thickness, the in-plane dipoles, so the states that contribute to out-of-plane dipole-like emission, they lose oscillator strength the more you confine. And this effect has to be combined with what we discussed before, with the effect of the dielectric environment. And if you do this, well, the picture changes significantly, even though please note that the anisotropy factor actually depends on the ratio between these 2 quantities. So in weakly confined nanocrystals, the effect is minimal, but you can see a big change in thin nanocrystals. And a final observation, which is quite interesting and specific of lead halide perovskites, is that since they have a very small Bohr exciton radius, the exchange interaction, it's very strong. It cannot be disregarded. And that's what leads to single triplet splitting of the band edge exciton. And not only that, but the shape of the nanocrystals affects effectively the fine states that compose the triplet state. And the interesting part here is that, as you can see, these are the out-of-plane and in-plane states which get split by the anisotropic confinement, and the difference between them is thickness dependent and is up to 16 millieV, and that's very, very close to KBT at room temperature, which means that we would observe such effects on the population of states even at room temperature. And a very interesting thing happens at very low thicknesses below n equals 3, where you have an effective reversal of the order of the states, which means that here the blue, the out-of-plane exciton, actually is energetically favorable in very thin nanoplatelets, and this has to be taken into account by the model. And here I can conclude by just presenting how we can put all these ingredients together and to try to understand what are the factors and try to predict the emission anisotropy from thin films of lead halide perovskite nanoplatelets. And you can see this was the picture disregarding electronic structure. This is the picture utilizing the full details of the electronic structure, and for sure, so nothing changed. It doesn't change very much at low, like high thicknesses, where it's weakly confinement, but there is a big change for very thin nanoplatelets. And if we don't consider those details, we severely underestimate this parameter. And also, we can see a strange effect which has to do with the bright triplet level reversal, is that very thin platelets below n equals 3, they have an anisotropy parameter which is lower than thicker platelets, which is counterintuitive. Why? Because the out-of-plane excitons now are energetically favorable. This for us was interesting to show that if you want to predict such, you could think of it as a more or less simple property of the thin film. Well, actually, you need to go quite deep into the understanding of the electronic structure of the nanocrystals, its electric environment, and how the assembly of these old nanocrystals play together. With this, I would like to thank all our group, especially the group leader, Professor Shi, who's in the audience, and
Is it? All right, good. Thank you for the invitation. It's actually nice to be invited for machine learning, even though it's not really completely my background. So today I'm going to present some of the work that we do in Erlangen, in Christoph Brabek's group, and try to use machine learning to make experimentation faster. And our goal on the long term would be to be able to use machine learning as a diagnostic tool so that you could give it solar cell data and it will automatically spit out, this is going wrong in the system, this is what you need to work on. So in my presentation, I have a lot of simulation results and some applied on experiments. So if you have a doubt about what is on the slide, I mean, typically when it looks too good to be true, it's simulation, but you can have a look at one of those icons to be sure. All right, so the philosophy that we follow basically is trying to have a research question and completely automate everything from experimental planning, from the sample fabrication, the automated measurement, and also the data analysis, and use that analysis as a feedback to drive that AI-helped experimental planning. Now, in the literature, there is actually a lot of effort that have been made into experimental planning, into using robots to prepare the samples, and obviously automated measurement. I mean, here we have some very good example where you can just plug in, press play, and it measures everything. But really what's not been looked at so much is a deeper analysis into the data, something that goes beyond just reporting efficiencies. And so that is what I'm going to try to develop. So in Erlangen, we actually have a quite amazing infrastructure that I think is really unique in the world in terms of capacity. So you have that Amanda line, which is where basically everything is automated, from the solution mixing to the spin coating to the evaporation to the device measurement and also degradation, and all of that in like a big glove box where robots just take care of everything. And this has a huge potential, because then instead of having PhD students working for hours and hours trying to make a few cells that are not even necessarily very reproducible, then you can make hundreds or 1,000 in a day or two. Like, you can really make like a year worth of work for a PhD student in a few days. Now, of course, you need first to spend the time to build such a system, but once it's running, you have a very high potential. And basically here you, well, can't see very much, but you have all of those platforms and to do degradation under temperature control, atmospheric control experiment. We can record a GV curve, absorption spectra, PL spectra, make some more fancy experiment if you want to add impedance and so on. And all of this is automated, saved in a database so that later on someone can look at it or also try to apply machine learning technique. So now this is nice, but when you make hundreds or thousands of cells in a day, at some point you need to analyze the data, and really this is a lot of data. So you need to get smart ways of looking at that data so you can actually get something useful from it. Because making device over devices is nice, but you also need to gain some understanding. And so this is what we will focus on during this talk. So most of the work I do is based on drift diffusion, so ZHAW-like method, even though, sorry, I don't use ZHAW. I actually use an open source device model. It's nice, it's free, it's not as fancy as ZHAW, but it works pretty well. And the comparison with ZHAW actually worked very well. I mean, with the right parameters. So basically in drift diffusion, as you've seen a lot, you can add different type of recombination at different places in your device. You can play with a generation profile. You can add ionic movements, doping, the effect of parasitic resistance. So you can really get a very nice and fine description of your device. We've used this in the past to look at OPVs of many different systems, binary, ternary, single carrier devices, same on perovskite. works very well. It takes time to get the right parameter set to reproduce the data, which is exactly why using machine learning would be so nice. So now my talk is like divided into 3 parts, where I'll try to go from fairly simple machine learning technique to slightly more advanced one. And in the first part, I'm going to be talking about perovskite, and then I'll move on to organic solar cells. So here the goal was to use light intensity dependence data to identify the dominant recombination process in a perovskite. And basically, when you think about this, it's really almost a simple classification problem, right? You have different possibilities. It can be bend-to-bend limited, bimolecular, if you prefer organic terms. It can be limited by grain boundary recombination, by the front interface recombination, by the back interface. And the goal really is to try to pinpoint that without having to do any extra measurement than light intensity dependence. And so to do that classification, basically our workflow was, we started with a very wide range of parameters that are still meaningful. We ran millions of simulation of light intensity dependent JV, and then we trained a machine learning model to be able to classify and recognize which type of data means which type of recombination. And then once that machine learning is trained, you can actually feed it experimental data, and it's going to do the same job. It's going to tell you, well, this is my limitation. To do that, I've tried many different methods, but the one that worked the best for me was using tree-based method. And those are actually very nice because they are very simple to grasp. It's not like neural network that can be a bit obscure. You can actually read through a tree. So, like, in very simple term, what tree-based methods are doing is you have a set of features, and if I take this example, for example, if you try to recognize what's an apple, what's a lemon, you can describe them with a certain set of features, like the weight, the skin roughness, the color, and you need to make a data set that is properly labeled, right? And then at each step in the tree, you are going to ask different questions. All right, is my fruit red? If yes, no, you go on one side of the tree, and then you go on up until you reach what is called a leaf, so a conclusion, where you've properly labeled what you're looking at. In that case, either a lemon or an apple. And so you can use that principle the same with light intensity dependence data. Now, one of the limitations of using such techniques is that, and I think this is true for almost all machine learning methods, is that you need a rather large data set. You need descriptive features of the label, and you need an accurate labeling. And very obviously, right, gathering that data on purely experimental data from the literature is close to impossible. So that's why using simulation to train those machine learning algorithms is so nice, because you know what you put in, you can make descriptive feature, and you have a very accurate labeling, and then you just need to try this on experimental data. So as a feature, basically, because you need to go slightly beyond just giving it a VOC, short circuit, and fill factor. One of the ones that was very natural to distinguish the different kind of recombination was the ideality factor, which is the slope of the light intensity dependence versus the VOC. I mean, on a log-lin scale. And basically, you can derive some equation, and if that slope is close to 1, it should be ideally purely bend-to-bend recombination or bimolecular recombination. And if it's close to 2, then you're dominated by trap-assisted recombination. Now, for anyone that works on perovskite, you know that most of the time when you make those measurements, your values is closer to like 1.4, somewhere in the middle. And that actually comes from very often from the fact that you're actually pinning one of the carrier density. And if one is pinned because of many different reasons, for example, you have a strongly doped transport layer, or some doping in a perovskite that sometimes happens, or you have a very thin transport layer and the density there is pinned because of the electrode density, then you actually reduce that ideality factor. So using ideality factor straight out of the gate is actually not so useful in perovskite because of that phenomenon. So you don't know if you have a mix of trap and bend-to-bend, or if it's a pin carrier density and so on. That's why you need to go a bit beyond that. And so this is some simulation I've done with different case scenario, where you see the evolution of the ideality factor depending on, for example, the trap density, whether they are at grain boundaries, front or back interface. And then you see that at some point you can reach values close to 2, but really in reasonable range you're going to see it somewhere in between. And so you need to be a bit careful. And there are many papers in the literature that actually use simply ideality factor to say like, when I degrade, I went from 1.1 to 1.5. That means that I have more trapping. That's not necessarily true. So you need to be a bit careful with those values. Now, as I said before, ions and doping can also have some effect. Ions, not so much actually. Because they move around nicely. Badly, but in that case, it means that it's not going to change so much. It's not really pinning a car. So now we generated a data set that kind of looks like this, where I have like many different data, and you can see that, for example, you have a very sharp peak for purely bend-to-bend dominated carriers. Then for the interface recombination, you tend to have somewhat low ideality factor, close to 1, but not really 1. And as you move your recombination more to the bulk of the material, then it can get close to 2. And you also have like different distribution for all the different parameters. And basically we use those values as feature to try to get to a conclusion. And those are only the one-son value, but we also used like the light intensity dependent one. However, in the light intensity dependent one, you also have to limit yourself a little, because if you go too low in light intensity, then those values are dominated by other effects like shunt resistance, for example. And if you go too high, then you're limited by shunt. So you really take a few values next to one son. So this was a conclusion just from doing that many simulation. Which is also nice, because then you can get a nice picture of what affects the ideality factor. And as you can see, it's not just what type of recombination dominates. It depends on many parameters. So you should not use only this to make a conclusion on your system. So now, coming back to the more machine learning part, like those trees look like this. And basically, like here my NW is the ideality factor. And you ask just question at each step. And so you can also like build up that tree, and here VOC 1 is the VOC at one son, and so on. And you can split them, and basically depending on how many you have in a certain place, you can know which is the dominant recombination. Of course here, because you can't really see very well on the screen, I've cut down the tree, but at some point you will arrive to endpoints where you have like a pure condition. So this is just one tree. Now the algorithm that we used that worked the best was actually random forest, which is basically you take one tree, you make 100 of them, you train them on sub-part of your data set, and they all reach different conclusions, sometimes all the same, sometimes slightly different, and then they just vote to decide what's the likeliest scenario. And this actually worked reasonably well. If I had 3 different kind of dominant recombination possible, bend-to-bend, grain boundaries and interface, I could make that confusion matrix. And basically, it was very efficient to recognize pure bend-to-bend, and then I had a bit more trouble with interface versus recombination in the bulk of the material. But it actually didn't do such a bad job. At the end, the accuracy of the prediction was about 80%. And realistically, when you look closer at the one that were mislabeled, it was like 95% of them were actually scenarios where the bulk trap-assisted recombination and the interface trap-assisted recombination were really close to each other in terms of which one dominate, which is why it's so difficult to properly label them, because realistically, they just contribute the same, so you could choose one or the other. And of course, like this is all nice on just simulation, but we also took some data from the literature that were already investigated by other techniques already fitted, and we fit those data to our little trees, and we looked if the conclusion was okay, and for this data, it was just giving exactly the right thing. And for this data that is very, very nice, also investigated with PL, we also reached like the right conclusion. It was telling us in like milliseconds, like, all right, your problem is at the interface. I couldn't find a nice way to see which one was bad, but at least you know you have a problem at one of your interface. So it's not a very advanced method, but it's still a very quick one that you can just have a look, and it gives you a clue where you have to work on. Then obviously the idea in the future would be to use those kind of simulation, probably of machine learning technique, probably more advanced, and to reach that kind of scenario where you do big simulation, you train your machine learning technique, and then you feed experimental data, and you can target your improvement. All right, now coming to the second part of the talk, where I've tried to use, again, slightly more advanced methods. I'm looking at organic solar cells, and I'm trying to really automate the drift diffusion fitting. Because if you've ever done drift diffusion fitting of JV curves and stuff like this, you know that it's actually not that simple. And it takes sometimes a lot of time, unless you're very lucky. And so we really need to do that, because coming back to our plan for the future with that automated feedback from the data, if we only limit ourselves to in measuring the efficiency, this gives a very weak feedback to the AI to know where it is going wrong. Like the AI is going to know that, all right, that condition goes wrong, but it's not really going to be able to see where. However, if you add that machine learning drift diffusion analysis, then you can really try to pinpoint more precisely where in the device, which material is going wrong. For example, if you look at organics and bulk heterojunction, for example, where you have two materials, if your drift diffusion fitting is telling you that the electron mobility is going wrong, then you know which material to change. And we could have used like simpler model to do that feedback, but you actually don't get enough information, and it would be, again, very weak as a feedback. You can't really make targeted improvement from it. Another problem of fitting simulation is actually, it comes from the fact that you have so many parameters. When you have the device, and if you just take a PIN structure, like you have thickness that you don't always really know precisely, dielectric constant, all the recombination parameters, the mobilities that are also difficult to get, the energy levels, and really how they align properly in all of the system. This is actually very important to make accurate fitting, but also experimentally very difficult to measure. And you can reduce some of them because you can have some measurement, or you can know at least the order of magnitude of many of them. But really one of the criticism that I don't know about you, but that I get very often when I do fitting is, it comes back to this, you have too many parameters, you can fit just about anything. And I've even had a reviewer actually cite this, like with 4 parameters I can fit an elephant, and with 5 I can make it wiggle strong. And our answer is, that's not true. If anyone has ever tried to make a fit, and like a good one, and you can make a bad fit, and yeah, sure, you can fit about anything, but a very precise one over several experiments, you know that this is not true. Now there is correlation between the parameters, but you can't just put anything. That's just out of the question. And I'm going to try to show that in the next few slides. And so to illustrate this problem that the JVs sometimes look very much like each other, here I have 2 JVs with different sets of parameter, and when I overlap them, well, they look the same, which is kind of problematic. If you fit that JV, you could reach any point, right? So these would not be sufficient. However, if you look a bit deeper, even though the JVs are the same, well, that ratio is also the same. So you can actually build up those well, I call them hyperparameter. It's a bad name because it means something else in machine learning, but it means that you can make those combined parameter of the singular one, and those one are very unique. And so you can see this here, for example. Here I'm plotting the RMS error versus two different parameters, the effective density of states and the bimolecular recombination strength. And if you really take those age, here you have a narrow parameter with the single parameter. So here you can actually use, if you only have two parameters, you can get both of them very precisely. But here you have to assume that you already know the mobility. If you don't know the mobility, this is what you get. Like, you have just so many of them that just could work. However, you can work out those hyperparameter figures of merits that physically make sense. For example, this one relates to the field factor and to the competition between recombination and extraction, right? So this is a very strong fitter. And you can define another one for the VOC on the right. And if you look at how unique your solution is with those figures of merit, you actually see that even if you don't know the mobility, you get a very narrow point, a very, very unique solution by fitting drift diffusion simulation to your JV. So if you really want a deep understanding of everything that happened in your system, well, maybe that's problematic. But as for us to drive and the optimization of our devices in that automated loop, actually those are the parameters that really govern your efficiency. So those are the ones that we are interested about to drive that optimization. And so for us, it is kind of sufficient to stop here. And so this is nice, and you can also look at this in the same way that Thomas presented a couple of days ago by using Bayesian optimization and Bayesian statistics. And you basically see a similar conclusion. If you have only 2-3 parameters and you know the mobility, you have a very narrow distribution on all of it, so you have a very well-defined solution. However, when you don't know the mobility, you see that it's somewhat flat for most of them. However, yet again, you see that you have a very defined distribution of what those figures of merit are and should be. Now, this is nice because you can also use this, like you can simulate or even do that on true experimental data. Here I simulated a degradation scenario where the mobilities were going down and the bend-to-bend recombination strength was going up. And you can make that fit, and you see that the mobility, getting the mobility right is difficult. Here, actually, you can even see that the electron and hole mobility are completely switched, right? Because I was simulating a very symmetric device, so it makes sense. However, you can get rather nicely those figures of merit, and you can obviously do that even if you have 5, 6, 7, 8 different parameters. And you can also like make those kind of graph where throughout the degradation you can follow how those figures of merit change and see what's happening in your device throughout the degradation. Now this is all nice. This was all on simulation, but I want to show that it also works when you look at experiment. So I took some PM6Y6 data that were aged in our lab, and I also tried it, and then you can fit it light intensity dependent fit. And you can again see how those figures of merit move around. You again don't get a very nice distribution on some of the parameters, but you can really see how those figures of merit change, and they give a very unique solution. So now, this is all nice, but the way Tonio Bionazzisi's group implemented that at the beginning, it's even at an earlier stage than what Thomas presented a couple of days ago. It was very inefficient, because you would actually take your entire material space, cut it into grid, calculate all the different points in the grid, and then kind of sum up the probability. So to make one fit, you would have to run like hundreds of thousands or millions of simulation, which is not very efficient. So what we are trying to develop now, and we are getting to the first versions that are getting selling now, is something that looks like this, where basically first you start with a lot of drift diffusion simulation, and you have your experimental data that you want to fit. Then you calculate a cost function which can be like your RMS error, for example, your MSE, or you can define more advanced one if you want. And then you have a Gaussian process regression that comes in here. And basically what this does, so first, Gaussian process regression is kind of a fancy-ish machine learning technique that is going to try to build a continuous function out of the data you're giving it, even though you don't formally know the function. So here you have like one of those very common picture in machine learning where you have like the true function in dashed, and then you can build up with Gaussian process regression some function to try to mimic the real one. So here that's what we are trying to do, but more in that case, because basically here those structure, basically we want to see the cost function. This is what we are trying to simulate with that GPR. So we are building a GPR to see how the error of your fit depends on the material parameter that you're giving it. So you get that multi-dimensional function that can predict for this subset of parameter, my error is going to be that much, without you doing the simulation. First, you need to train it on sufficient data, but then you can basically cover a very wide parameter space without having to simulate everything in there. So this makes, obviously, the computational time a lot faster, and then you do some Bayesian optimization actually on that trained GPR, on that fictive function, and it's the Bayesian optimization is going to try to look for that minimum in the error. And so instead of looking at only it's only experimental data where you had some here and there to track, you actually build that smoother function and try to find a minimum of that function. And then, of course, then you see if you have a good fit. If you don't have a good fit, then you do another run of simulation, you train another GPR, and you again try to find a more defined minimum. And you can do that, and instead of having to run thousands of simulation, I can decently fit some system with a few hundred, which is like a huge win in time. Here are some examples. I don't think you'll be able to see that so much, but basically this is the same than presented before, where here you had like 2 free parameter. You have a very narrow solution. That one is actually correlated. You see that slight kink. And this is with the figures of merit where the minimum is actually here so narrow that you can barely fit because it's very, very small and very steep minimum. And I've tried this obviously on experimental data with a bit more fitting parameter, and I can basically get results as good, if not better, than presented before, but a lot quicker. Like instead of needing a full night on a big workstation, I can get this in like maybe 10 minutes. And then at the end you can make graphs like this where you see the evolution of the different parameter. Here it's just the number of measurement in time. And what's nice with doing that with Bayesian optimization and Gaussian process is that you can actually also get some error bars into the parameter that you estimate. So to conclude here, like we've tried to build that infrastructure where we don't have by hand to fit everything, and where we can extract the parameter very fast. And it's also very flexible because you can put in any kind of device structure. You don't have to do like Thomas did, where you're somewhat limited by how you've trained your neural network. How much time do I have left? Oh, that's a shame. It's okay, it's okay. All right, so to like the true conclusion in there, and where I would really like to go in the future is to have kind of a suite of different machine learning methods that would help you to get to a solution faster. And I think the first step should be in classifiers, because you have potentially a lot of device parameter to fit, but also different models, like whether or not you have traps in your system, whether or not you have ions, and all of those. And if you can actually remove those parameters from the fitting space, you win a lot of time again. So the classifier would come first and tell you like, all right, this model is the most probable, and then only you go on to fit it. Now, I haven't had the time to show it, but you can also, as Thomas described, build surrogate model where you replace the drift diffusion by a neural network, for example. And that can also work very well. In what Thomas presented, it's somewhat, you're kind of stuck into the device structure that you simulated. But for some other experiment, it doesn't matter as much, and you can make it very flexible and still very efficient. And with this, I'd like to thank all of the people that have worked on this, whether it's my time during my PhD at the University of Groningen or my time now in Nuremberg, Erlangen. And thank you for your attention.
Simulated imaging data.
Yes, thank you for the introduction, and I think it's actually a really nice fit or a nice follow-up talk for the previous talk that we heard, because we used very similar concepts in our work in a little bit of a different setting of imaging data. So yeah, my talk is called Solar Cell Parameter Extraction by Convolutional Neural Networks Trained on Simulated Imaging Data. And this work is inspired by all the reports on how successful neural networks are, especially in the field of image recognition. So we thought, why not use it in our field of PV cell modeling and see what we can get out of it. In our group, we work with the LAWS model. Ennio has already presented it in his talk on Wednesday, so I'm just going to briefly summarize it. The model uses a 2D plus 1D approach, in which the top and the bottom electrode of the cell are modeled as 2D domains on which Ohm's law is solved for a given sheet resistance. And then the two electrodes are coupled by a 1D coupling law that includes all the electrical and thermal behavior of or characteristics of the cell. Then with this model in hand, one can calculate all sort of interesting cell characteristics, such as the IV law, or as Ennio has explained, the small signal dark lock-in thermography image, but also electroluminescence images, for example. So where would we now use a convolutional neural network in this case? Well, I mean, in most cases, when you work with such a model, you have some measurement data, and you want at first fit the measurement data to the model. And you can do this with traditional optimization algorithms, but sometimes that's not so easy because you, it can be quite time-consuming, and you can also get stuck in local minima, for example. And this is especially true if you have this very high-dimensional data of, that images provide. So our idea was to actually use neural networks to perform these steps, meaning taking an image as an input and provide you with the model parameters as an output. And when I say, we used EL images as an input, which is not 100% true actually, because if you look at what the EL signal is, or where the EL signal is coming from, it's actually proportional to this exponential of the junction voltage of the cell multiplied with some calibration constant. So what we did some pre-processing. We measured the EL image at 2 different voltages, and then we're able to, by using the contrast of those two, kind of canceling out the calibration constant and calculating this junction voltage. So all the images you will see in my talk are actually these kind of junction voltage images that we calculated from the two EL images. Yeah, as it already was mentioned before, in order to make machine learning work, you basically need a lot of data, meaning really a huge number of data points. And unfortunately, also in this application, that's not so easy because, I mean, you would need a lot of EL images of cells that have very different characteristics. And then you would also have to measure these characteristics, which is also unfortunately not very straightforward. So what we as well did, we simulated the training data by LAWS itself. So we fixed some cell geometry, that we had some measurement samples that we were interested in. We introduced some random shunts, and then sampled LAWS model parameters out of a predefined parameter range. And of course, we also had to define which parameters we want to look at. In our case, since we only had EL images, which was kind of limiting, we only looked at 4 parameters, of which we thought, well, they could maybe be predicted out of the EL image, and those were the applied voltage of the higher voltage EL image, the dark saturation current, J0, the sheet resistance of the cell, and the parallel resistivity of the cell. And all the other parameters were fixed, so that we had a little bit more an easy problem. And then as a test, if this model works, we applied it on measured data, and to get the parameters out of the measured data, and then use these parameters to resimulate with flaws again and see if the two images actually match. And if they match, it's a sign that this method is kind of working. Of course, not all the parameters of the cell have the same, not all the areas of the cell have the same parameters. So we dealt with this by introducing a second channel in addition to the EL image that we gave the model as an input. And this second channel contained a mask that kind of tells the model where it should look at for this particular case. So yeah, for which region it should predict the parameters. So this basically means that for each image, or I mean in this case we had three different areas: the active area, just a normal active area, the grid lines, and the shunt area that we introduced. So this would mean that you have to apply the model 3 times to this image with different masks to get the complete parameter set out of it that you then can use for resimulation. Yeah, training a neural network basically means applying a stochastic gradient algorithm that minimizes the loss function. It just optimizes the weights and biases of the network such that the loss function is minimized. For regression problems, it's common to use, for example, a mean squared error. To add a little bit of more scientific flavor, let's say, to our project, we used another loss function. That's the negative log probability loss function. That means that the model does not output a single point prediction, but the mean and the variance of a Gaussian probability distribution for each parameter, which gives then the model the freedom to not only decrease the loss function value by predicting better, but in cases where there is insufficient information, it can just predict the higher variance, and then the loss function will decrease as well. And it gives then the user, or in the end, the information, okay, in this particular case, it's most likely the prediction is not really accurate. And the result of the training in our case can be seen here in the right-hand side in these comparison plots where the true value is on the x-axis and the predicted value is on the y-axis, including the standard deviation predicted by the model. And you can see that the training seems to work reasonably. You can also see the parameter ranges that we used. And you can also see that this negative log probability loss actually seems to work, because if you look at the plot for the dark saturation current, the values that are off the diagonal and thus have a prediction error also have a higher predicted variance. So the model seems to identify like cases that have insufficient information correctly. But as I mentioned, the real test for this model would be to apply now measured data and see if this actually works and gives reasonable results. So here I show actually 2 measured samples that we used for testing, and one validation set image that was simulated as well, just for comparison reasons. And we can now apply the model on this data and see what parameters that we get. And in the case of the simulated image, we of course know the original simulation parameters, so we can do a comparison. And that is this blue data point, and which is the predicted probability distribution, and the black cross, which was the original simulation value. And we can see that for the applied voltage, this kind of worked, and also for in the lowest plot for the parallel resistivity of the shunt, but for the dark saturation current and the sheet resistance, values are quite off. And this is, of course, also, it was also mentioned before, these 2 values are highly coupled, and it's not really possible to get them independently out of the ELM image alone. And I will talk about this in a minute a little bit more. So then we can use these parameters to resimulate with laws again and compare if the images look alike. I would say, yeah, more or less, not 100%. So it's also good to look a little bit in more detail in another visualization. So here we have horizontal and vertical cross-section through the shunts. So it's basically a cross in this direction and in this direction. And we can see that especially in the normal active area parts with the grid lines, it seems to be the measured image seems to be reproduced quite well, and the highest differences are actually in the shunt area. But as we have this information from the probability distribution of the parameters that we predicted, we can also kind of calculate the image probability distribution. And we did this with just a normal Monte Carlo sampling. And then we can see that also in this shunted area, this light blue standard deviation of this image probability distribution actually also covers the measurement. So at least the model knows where the insecurities are, it seems. So yeah, it seems to work reasonably well, at least like to reproduce the EL image with this approach. But there are some issues that I want to address, and one of which is that since we use simulated data for training, it's very important that this simulated data actually covers the range of images that the model will see in the end. For example, in this case, we have measured images that show features that are not present in the training data, and especially this is true for the shunts. So we put a lot of effort in trying to model these shunts, or the shape of these shunts that we measured in the EL image and to reproduce them in LAWs, and this was not 100% successful, so we had some differences. And this leads to out-of-training sample prediction by the CNN, and that's a very inconvenient feature of neural networks, that if you're out of your training sample, it can basically do unexpected things. You're not really in control anymore. So the solution for this would be to just further improve this training data generation and put more effort there. I think that's one of the most important thing of such an approach, to be very close to the measured samples that you want to predict in the end. And then the other thing, of course, as we have already heard in the previous talk, is that, predicting parameters from EL images alone, I mean, it's a bit a poor man's approach, I would say, because, of course, there are a lot of parameters that are not or cannot be estimated independently from an EL image alone. So if you look at this governing equation that is important for the EL image in LAWs, we see that, for example, the sheet resistance and the dark saturation current, they just show up as a product, especially, or at least in the case where you have no photo generation current. So yeah, this basically means that these two parameters are coupled. This is also what we have seen before in the model output, that the two parameters have been they were predicted off, but in the end, the EL image was still reproduced correctly, and this is because of this parameter coupling. And of course, the solution to this is to just add more data, other measurement methods, like the IV curve, a PL image, or maybe a dark lock-in thermography image, to have a more extensive basis to do this parameter prediction. And this is what we want to do next. So we are now developing an all-in-one imaging set device that allows us to combine EL, PL, delete, SS delete images, and also the IV curve of the cells. And essentially the way, I mean, the most important way is to record all these images in a way that it's easy to merge them in one single data set, and that allows you to feed them into your model and get nice results. And it's not so easy because imaging data, I mean, everything has to be perfectly aligned and so on. So yeah, we're working on this at the moment and hope that this will improve our parameter estimation. And then another thing that we're working on is that we want to replace this conventional CNN architecture with physics-informed neural networks, and this will be addressed in the next talk by Evelyne. So it remains to thank you for your attention, and thanks to the institutions and people who made this work possible. Thank you.
Thank you, Mattia.
So thanks for the introduction, and I think we have already caught up on most of the machine learning topics. So hopefully I can introduce something new in my talk. And first of all, let's look at data from a machine learning perspective. What is valuable data? And this is the volume of data created, captured, copied, and consumed worldwide. So in the year 2020, we are roughly around 100 zettabytes of data. So we are all better with the small numbers. So here you see zeta is 10 to the power of 21. So if this was the amount of gold, it would be worthless by now. So why is this data valuable? And only high quality data is valuable. So in machine learning, high quality data is labeled data or annotated data. If you're looking for a definition of high quality data, you get something like this. Data is generally considered high quality if it is fit for its intended uses in operations, decision making, and planning. So basically, if you get the information out of the data, then it was good data. But that's all I found. So I'm trying to make the link to the elephant that Thomas showed. If you're just working here on the tail, you maybe have too little information in your data to get the entire picture, so you need more data from the entire elephant. So machine learning won't do any magic. It won't find information that is not in your data. But maybe it can assist us by giving us additional tools, methods, frameworks, whatever, to investigate the data. So instead of just touching, maybe you can use your other senses and make more out of your locally confined data set. So going back to a more realistic problem, moving away from the elephant. So I think the problem has been well introduced. We want to do a fit. So here are 9 experiments for a perovskite solar cell in black the measurement, in red the simulation. You basically see the model fits the data in the 9 experiments. It's not a perfect fit, but it kind of captures the main feature. So how can we take advantage of machine learning to get such fits? Usually we're in this top left corner. We have a physical model. We quite know the equations that we want to solve. We have small data in terms of initial condition or boundary conditions. When we do machine learning, we're down here. We need a lot of data, and usually we have no physical model. We have a general machine learning model. So this brings us to the fundamental problems of classical machine learning for problems in physics. And one is you need a lot of data. Either you spend your life doing experiments or searching publications for data or running experiments. Second point, we heard it already, you cannot extrapolate out of your training data set well. And the third one, it's hard to understand. So the tree models might be one of the exceptions where you kind of get a notion what is going on. So the goal would be to go to this sweet spot in the middle. You have your data and you know the physics. And here are some of the advantages of physics-informed machine learning. Our problems in physics are often highly structured, and we can generate new data. We can do more experiments when we feel that we need more experiments or simulation at a certain point. We can use existing physical models as initial guess or as constraints. So let's focus on this. And in the previous talk, we saw that we used the physical model to generate the data till we had a lot of data, and then we kind of forgot about the physics to extract the parameters. So maybe we can find something in between those two extremes. And here I would like to introduce physics-informed neural network. It's a new research field, I would say, in short, PINs. So they consist of a neural network, which is a universal function approximator. Additionally, we embed the knowledge of the physical law, usually in the form of a PDE or multiple PDEs. And this prior knowledge of physical law, that helps us in training because it regularizes, it acts as a regularization term when we train the model, and therefore limits the space of admissible solutions and gives more meaning to the data available. And also it generalizes well, even with a low amount of training examples. So I will show my first steps with the pins, and also I'm using the model that was introduced by Inyo and Mattia. So the 2D plus 1D approach, the 2D electrodes that are coupled by a 1D model. Here we have the boundary condition that we apply, a Dirichlet boundary condition on the left side, so 0.8 volt. On the rest we have a zero flux boundary. And here we grounded the cell. And if you look at the sheet resistance, the bottom sheet resistance is very low. So here we have a very good conductivity, whereas in the top we have a value of 95 ohms square. And the two electrodes are connected by the one diode model that you see here. And yeah, I just filled in these parameters to basically get a simulation tool. First of all, I solved it with the FEM approach, so nothing to do with the pin yet. And yes, solved the equation. What I got was a potential distribution on the top electrode. And as already mentioned by Mattia, eventually we can combine this with the electroluminescence images, and that's what we actually want to look at in the end. So if we now look at a comparison between FEM and PIN, so on the left again the FEM result. If we take a cut and reduce it to one dimension and compare it with the PIN, we actually see that the two results agree pretty well. So in the following, I will stay in the 1D regime for the PIN. So basically for every point here between 0 and 1, so this is the space variable, I get a value for the potential. So now I'd like to explain how we actually get the solution with the PIN. So what we need is a neural net. We have as an input our space variable between 0 and 1, and it approximates our potential, and for each value in space we get a value for the potential. We can take advantage of automatic differentiation, so we can this function approximation, we can take the second derivative as given here, so in 1D it reduces to the second derivative, and then we make sure that this equation is fulfilled. So basically we sample a few points and then we look at how big is our residual of this equation. When we start and initialize the neural net, this will hardly be 0, so we need to get this loss term as, we need to minimize it or to get it as close to 0 as possible. So basically, when this equation is fulfilled, we are on the safe side that we are looking at the right physics, so we want to minimize this loss term. But also, we have to consider the two boundaries, and once we have a Dirichlet boundary condition and once we have a Neumann boundary condition. So we have to make sure that we have the pre-described potential that is fulfilled here. If it's slightly off, it contributes to the loss term, the same for the Neumann boundary condition. So we add this all up, and this gives our total loss. By varying the weights and biases in our neural network, we can minimize this loss function. In a second round, we sample the points again and look at our losses again and keep doing this until we have a good approximation of our potential. So this is the forward problem. But in the fitting problem, we are actually interested in the inverse problem. So we want to find out the parameters in red. But I'm also given a EL image or a potential distribution from a simulation. So this is this extra term now for the inverse problem. Here is my function approximation that I get from the neural network, and I subtract the measurement or simulation or whatever I take as a reference. And I try to minimize this error, so I will add this also to the loss term and keep minimizing the entire loss. So this offers me a seamless integration of my measurements into my neural network. And here I'm showing a small toy example. So here is a forward simulation. I used certain values for the sheet resistance, dark saturation current, and ideality factor, and parallel conductivity. So basically here you see the 2D distribution on the electrode of the potential, slightly different boundary conditions. So this is a simulation, but in the end we will use an EL measurement, but just for training and sanity check, this should do the job. So now I apply my PIN, and what I want to do is I want to find these 4 parameters. The PIN returns me 4 parameters, and I put it back into the FEM simulator to see what comes out, and basically I get the same picture again. So one would think, okay, it kind of works, but when we actually look at parameters and I plot the entire coupling law multiplied with the sheet resistance, we see the parameters are different. But in this area here, around 0.8, that's where most of the potential distribution is. We get a good agreement because here the two functions cross one another. So the obvious step is don't just use one image, maybe multiple voltages would be helpful. And also if we look at the formula here, we see the correlation that Mattia already mentioned. So I also added a JV. And here what you're seeing is in black the noisy measurement. So the noisy measurement is the FEM simulation with some white noise. And in blue you see the pin that fits fine for all these distributions. So here I used 6 different situations, and I also added the JV curve. So here are actually always 2 points on top of each other because the fit is so good you can hardly see them. So for each potential distribution I also calculated the current and fitted it. So basically what we see is that we can minimize the correlation when we add another experiment here, the JV, and the parameter that I extracted now, they exactly agreed. The only challenge that remains is to get the neural network to converge, because we have multiple loss term and the gradients sometimes are competing, so you need to weigh them in a good manner and find a good strategy. So this is still ongoing research, and it's going on in the field of scientific machine learning. And I hope I could convince you that pins offer a good option for a seamless integration of measurement data. For the forward simulation, we will probably stay with our current methods. And for us, our next step is to use EL measurements instead of my artificial measurements made by simulation. Last but not least, thanks to everyone mentioned on the slide and to you for still being here on a Friday afternoon.